My name is Baron Ha, and this is my lab tube magnetic field of a bar magnet. Introduction is that we're going to measure the distance dependence of the magnetic field of a small bar magnet and compare that to the computations of on-axis and perpendicular axis calculated by the Biot-Savart law. And we're going to use the magnetometer app to find the north and south, east and west poles of the Earth's magnetic field. The purpose of this experiment is we're going to find the relationship between the distance and the magnetic field strength, compare that to the magnetic field calculated by the Biot-Savart law, and use glow script to represent the magnetic fields. Fundamental physical principles of a general Biot-Savart law, the distance dependence of magnetic field of a bar magnet, and the dipole on axis and the perpendicular axis. And a brief preview of the lab results, which I will go over on later, is the n value is negative 2.7178. The magnetic dipole value is 3.483, should be amperes times meters squared. And pre-experimental things that we have to do, we have to calibrate the x-axis to be 0, which is the red line there. And given the latitude and longitude of my location, the net magnetic field should have been 40.114 microteslas. And in the rightmost screenshot, it is 38.66 microteslas. And finding the magnetometer chip, which I'll go upon in the next slide, is on the bottom right corner. An experimental setup to find the magnetometer location is you put your bar magnet on one end of the east-west oriented meter stick, and you slide your phone perpendicular and find the point where the absolute value of x is the greatest. And at that point, you're going to tape parallel to the meter stick, and then you're going to do the same thing, flipping it 90 degrees because you want to do the other axis. And you repeat those steps again. And after that, you should get the bottom most photo where you have an intersection of 2 points, and that is where the magnetometer chip is. With the measurements on axis, the system is the magnetometer and the surroundings is the bar magnet. And when we found the n and the mu value, we used the B equals KRN, which is the distance dependence equation. And we also use the on-axis equation, which is mu naught over 4 square or 4 pi 2 mu over r cubed equation. And by doing that, we found the n and the mu value. And for example, and for the data on the right, what these points mean is, like, for example, R20 in the topmost is R20 is like 20 microteslas, like how far that would be to exert that force. So for example, for R20, it would be 0.27 meters, 0.32 meters, 0.28 meters, the 3 different experiments that I did. And measurements off axis, all these calculations done through Excel, but basically we use the off axis or the perpendicular axis equation for the dipole 3 slides previously, and we found the B net to be magnetic field net to be 0.0001 roughly. Coding part 1, basically what we did here was 2 on-axis arrows and 4 perpendicular axis arrows, and as you can see, the perpendicular is like negative and roughly like 2 times less, because in the equation of the perpendicular axis it's negative and there's no 2 in the numerator. And then the B at 45 degrees is vector form 1.43 times 10 to the negative 5, comma 4.3 times 10 to the negative 5. And similarities and differences between the models is that the experimental model was a lot bigger than the computational model, and the assumptions were that no external magnetic forces in the computational model. However, the differences led to like possible sources of errors. For example, magnets in the surroundings could have affected the experimental model, and then the precision of finding the center of the magnetometer wasn't that precise. The technology in the building has a lot of magnetic objects, and then there also could have been imperfections within the magnetometer app. Discussing questions: what if we didn't compensate? We compensated for the magnetic north, and we instead laid out the meter stick at an angle respect to Earth's magnetic field. And because Earth has its own magnetic field, it would be less accurate. And if we had 2 identical magnets and we used them stuck together end to end instead of a single magnet, the magnitude of the magnetic field would be doubled, but it would still be in the same direction. And the conclusion is when the magnetometer is far away, there's barely a magnetic field in the x direction. As the magnetometer moves closer, the x direction fluctuated, and as the distance increased, the magnetic field exerted by the bar magnet